Thank you for coming back to part 2. We're going to take what you learned in part 1 and build on it with some more advanced concepts. We're still going to stick with IPv4 only throughout this video. At the end of part 1, we talked about classless interdomain routing, or CIDR. That's where we use a subnet mask to break a network into smaller, better-sized subnetworks. This helps us to conserve IP addresses. We can build on this by introducing to you a concept called Variable Length Subnet Mask, or VLSM. This helps us to conserve even more IP addresses. Let's take our 172.16.00/16 network as an example again. We previously spoke about breaking it up into 256/24 networks. We did this because we had several smaller offices rather than one large one. Now, we have 256 IPs in each network. But we also have links between our offices. These are also a kind of network. They may be very small though, with only a router at each end. No printers, workstations, or anything like that. If these networks are all /24s, we're wasting over 200 IP addresses per link. What we can do instead is choose one of our /24 networks and break it up even further. Maybe we could break it into /30s. A /30 network uses 30 bits for the network and 2 bits for the host. That's 4 IP addresses in each network. This allows for our 2 routers with 2 IPs to spare. I'll talk about why we're keeping 2 spare a little later on. Now, our original network, 172.16.00/16, has been broken into subnets of different sizes. Some are /24s and others are /30. And that's all VLSM is. It's creating subnets of different sizes. All the IP addresses that we have spoken about so far are addresses that are assigned to devices. As you know, these are also called host addresses. Often our devices only want to send traffic to one other device at a time. This is called unicast traffic. You can think of this as being in a room full of people, and you single one of them out, and you have a conversation with only one person and ignore everyone else. But that's just common sense, right? Isn't traffic always between 2 devices? No, not always. Sometimes a device will want to send a message to every other device in the local network. This may happen if it wants a particular resource, but it doesn't know where it is. It may broadcast a message asking, "Who owns this resource?" or "Where can I find this?" As I've just hinted, this is called broadcast traffic. Imagine you're back in that room full of people, and someone gets up to the microphone and makes an announcement. They're sending a message to everyone at once. To broadcast to every device, we have a special IP address. I'm sure you won't be surprised to find that it's called the broadcast IP. So which IP is the broadcast IP? It is the very last IP in the local network. Always. The last IP address is the IP where all host bits are turned on. Taking the 172.16.2.0/24 network as an example, the last IP is 172.16.2.255. So, as this is special, you can never configure a device with a broadcast IP. And while we're talking about addresses that you can't allocate to devices, there's another one, and that's called the network address. The network address is kind of the opposite of the broadcast address. It is when all the host bits are set to 0. So, 172.16.2.0/24 is a network address. Remember just a few minutes ago when we said we can use a /30 network between our offices? I said that we would need 2 addresses to spare. That's because of the network and the broadcast addresses. A skill you will want to develop is working out what these addresses are in any network, as well as how many addresses you can actually use. Let's take an example. You have a device with the IP 172.16.0.10/24. From the /24, we can see that the first 3 octets are the network and the last octet are the host bits. If we set all host bits to 0, we have 172.16.0.0. That's the network address. If all the host bits are set to 1, we have 172.16.0.255. That's the broadcast address. 8 host bits mean there is a maximum of 256 addresses. We subtract our 2 special addresses and find that we have 254 usable IPs on this network. Now that's not too hard to work out on a /24 network, but when VLSM enters the picture, it can get a little more complicated. Imagine that a device has an IP of 10.42.37.12/22. This is a much more complicated example. While you can sit down and work out all the different ones and zeros, there's another method that many people find easier, and it's called the magic number method. We start with our IP address and we work out the subnet mask. A /22 has 22 ones, so we get to a subnet mask of 255.255.252.0. Now find the octet in the subnet mask that we need to work with. It's going to be the one that's got a mixture of ones and zeros, so the 3rd octet in our case. Subtract this value from 256. For us, 256 minus 252 is 4. Now we need to know the value of the 3rd octet in our IP. That's 37 in our case. We count by 4 until we find the numbers that are next to the value of the 3rd octet in our IP. That means we want the numbers immediately smaller and larger than 37. If we count by 4, that's 36 and 40. 36 is the start of the network. That gives us the network address. 40 is the start of the next network. So we can go back 1 IP and that gives us the broadcast. We know there are 10 host bits. That gives us 1024 IP addresses. Subtract our 2 special addresses and we have 1022 usable IPs on this network. Now that is a lot to take in. Go over it a few times and practice. In fact, try a few right now. See if you can work out the network address, the broadcast address, and the number of usable IPs for these networks here. We know that the router helps to get traffic from one network to another. We also discussed how a device knows when to ask the router for help. But how do devices find the router? How do they know where to send their traffic when they need help? When we configure an IP address on, say, a Windows machine, we will also configure a default gateway. This is the local router's IP address. So, when a host has no way of sending traffic to its destination on its own, it will forward it to the default gateway. Some devices call the default gateway the gateway of last resort. I kind of like this term because it really shows us what this IP address is for. If a host runs out of options to handle the data itself, as a last resort, it sends it to the local router. Let's go back to broadcast traffic for a moment. I said earlier that the last IP address in the subnet is the broadcast IP. It's not the only one. There's another special IP used for broadcasts. It's 255.255.255.255. It's different in that it doesn't care what the local subnet is. It basically says, I don't care what network you're on, send this traffic everywhere. There are times when this is useful. One case is when a host is starting up and it doesn't have an IP address yet. We'll get into this a bit more later, but one option is to use a special server to give the host an IP address. But the host doesn't know where the server is yet, so it sends out a broadcast to 255.255.255.255 asking for an IP. So while it's useful, there are also some downsides to broadcasting around like this. Routers are made to forward traffic between networks. So what would happen if they received a broadcast? Well, the larger network could get flooded with broadcast messages. Also, if a broadcast message gets forwarded from one router to another router, it may get stuck in a loop. The simple solution to this is routers never forward broadcast messages. All IP broadcast messages stay within the local network. That makes us wonder then, what if we do need to announce something to other parts of our network? An example of this might be a server that's sending a video stream. Several devices in the network want to tune in and watch this video stream. One option is perhaps we could send video traffic to each device individually. That's the unicast traffic we discussed before. Unfortunately, that's inefficient because we would need to duplicate this traffic for every single recipient. Broadcasting is no good for two reasons. First, not all devices want to receive the stream. I mean, what would a printer do with a video stream? Second, broadcasts don't get past the router. So other subnets would not be able to receive the traffic. The way we make this work is with a technology called multicast. Multicast uses special IP addresses. We mentioned this back in the last video when we spoke about Class D. These addresses range from 224.0.0.0 to 239.255.255.255. We won't get into much detail here, but basically multicast is a way for devices to opt in to receiving certain traffic. The video server sends traffic to a multicast IP, and other hosts look for traffic sent to that IP. Routers also forward multicast, so the traffic can reach the networks it needs to get to. So imagine you're back in that room full of people. If all of you broke out into small groups and you spoke to your small group while ignoring everyone else, then you're multicasting. This is a lot of information to take in, so see if you got it all. We just spoke about 3 different special address types. Can you remember what they are and how they work? IP addresses need to be unique if they are to work properly. It's like your home address. If someone somewhere else in the country has exactly the same address as you, your mail might end up at their place, or their mail may end up at yours. So how do we make sure that the IP addresses in your network are unique? What's to stop someone else in another company using the same addresses that you have? IP addresses are managed by an organization called the Internet Assigned Numbers Authority. They give large blocks of addresses to sub-organizations around the world called regional internet registries. Each RIR has a different name. The one that we use here in Australia is called the Asia Pacific Network Information Center, or APNIC. The RIRs then assign blocks of IP space either directly to you, if you're a large enough customer, or they'll also assign blocks to internet providers. Then ISPs, the internet providers, will give some of their space to the smaller customers. While this process is a necessity, there are some problems we'll face. If you want to create a new network, you may need to get more IP space, and that can really slow you down. Also, we use up IP space very quickly. As we have already seen, we run into problems when we run low on IP addresses. So, to address these issues, in the mid-1990s, a standard called RFC 1918 was released. If you're not familiar with RFCs, they're standards that describe how certain internet technologies work. I'll include a link to one of them if you're interested, but be warned they're very detailed and sometimes quite complex, so don't feel obligated to have a read. Anyway, this particular RFC says that some IP spaces are now reserved for private use. You can use these IPs in any way that you see fit within your local network. All other IPs, these are the ones that are assigned to you or to the ISP, are called public IPs. Remember these IPs, the ones you see on your screen here, you will see them a lot in your daily life. But there's something interesting about these addresses. They are not allowed on the internet. Why? Well, this prevents us from overlapping with any other company that is using the same addresses. It also conserves IP addresses, as we don't need to use so many public IP addresses anymore. But if they're not allowed on the internet, how do you get access to the internet? Even with private addressing, you still use some public addressing. At the very least, your internet provider will give you one public address. Let's say you have a device in your network with the IP 172.16.0.1. When it sends a message to the internet router will alter this message to use a public IP address. This is a process called NAT, or Network Address Translation. It's a topic all of its own, so I won't go into any more detail on this right now. We'll cover that in another video some other time. Let me propose this simple question. Which RFC defines private addresses? Which private address ranges does it define? We'll now take a moment to talk about how devices get addresses. There are two main ways, and one less common way. First, you can log into a device and configure an address. This is called a static address, as it doesn't change unless you manually reconfigure it. When you assign an IP address this way, you need to choose the address, and you need to make sure it's unique. If two devices end up with the same address, we'll have an IP conflict, which causes us all sorts of problems. You will commonly use this method for devices like routers and some servers, devices whose addresses should never change. The second method is to set addresses dynamically with a DHCP server. A DHCP server has a pool of IP addresses available to it. When a device starts up, it broadcasts a message around the local network to find the DHCP server. The server then gives it an IP address from its pool. The server makes sure that it doesn't give the same IP address to more than one device. Also, there's no guarantee that the device will get the same IP address each time. That's part of what makes this process dynamic. This is good news for workstations, laptops, phones, and tablets. These are devices that may be mobile, and will need to get a new address whenever they move to a new network. There's also a lot of these devices, so it's an easier method than logging into every single device and configuring them manually. Now the third method, it's a little unusual. It's called automatic private IP addressing. And as far as I can tell, only Windows uses it. The basic idea is, you don't statically set an IP address on this machine. The workstation starts and sends a broadcast message to find a DHCP server. However, it doesn't find one. This is when APIPA, did I get that correct? APIPA, yep, that's right. Now, that is when APIPA kicks in. It picks a random IP from the 169.254.00/16 space and assigns that to the workstation. This kinda has its uses. Perhaps on a small network, if the DHCP server fails, then devices can still reach each other. They won't know what their default gateway should be, so they won't be able to reach other networks or the internet, but at least they can reach each other. Personally, I would not recommend relying on this method. When we looked at the OSI model, we learned how extra headers are added to the data before it is sent. This adds information needed for delivery. It's like writing an address on an envelope. IP is no exception to this. It adds the header that you see here. Not all the details that you will see will make a lot of sense right now. We'll cover a few of the fields, but we won't get into a lot of detail. For now, the two important parts that you need to know are the source and destination fields. And they're pretty self-explanatory. The version field is also easy. It's either for IPv4 or IPv6. Now, this is where it gets interesting. Sometimes a packet is too large for a particular device. So, the device will break the packet into smaller packets and send each of them individually. This is called fragmentation. So, this field here, the fragment offset, tracks the order of these fragments so they can be reassembled in the right order at the destination. But sometimes we decide we want to prevent fragmentation altogether, and we can do that by using the flags field. Here's another interesting one. Remember earlier I said that broadcasts could go round and round and round in circles if routers didn't stop them? Well, the same could happen to other kinds of traffic. So to deal with this, we have this time to live field. The device sending the packet sets a value in this field. Every time the packet passes through a router, the TTL value is lowered by 1. If it gets all the way to 0, the packet is dropped. This is how we prevent a packet from looping forever if there is some sort of error in the network. Next up, we're going to look at the TCP/IP model. This is somewhat like the OSI model, but it has a bit of a different approach. Let me know what you thought of this video in the comments, and subscribe if you don't want to miss anything new.